So we have this thesis that the usefulness of AI is, and specifically agents, it's roughly proportional to their access to your personal data. Right? So as an AI, if you give it access to intimate details about yourself, we're on the verge of a future where each of us have this like personal executive assistant, not just one, but a fleet of them that can be monitoring all of our information channels, from what we're doing on our screens to remember like what we did last week. What was that document I read? Being able to find and do that kind of retrieval, to looking for outliers in our healthcare data, our biometrics, our monitoring our social media feeds, surfacing up relevant content, right? This excites me because there's a lot about my day-to-day life, just like with ADHD, executive dysfunction, having something that can go like dive down into all this and organize that and surface relevant content up to me as I need it sounds pretty appealing. But as I'm going through this list of data that I think AI is going to want access to, some of you might be getting a little bit uncomfortable. And I know, at least for me and all like a majority of my friends who are not in tech, when I go on these kinds of rants, they start getting like deeply comfortable. They're not exactly down for this future. And that's because what this future kind of looks like is that these AI products are really getting root access to our lives. And it stops looking like, the Facebook and Google and large tech companies of today, where our data is partitioned across multiple vendors. It's still pretty intimate levels of detail, but this is root access, where the same company that has access to your social communication is also recording your screen 24/7 and also has access to your healthcare data and your biometrics. And that's kind of starting to look like a 1984 telescreen. And that kind of freaks me out. And this is why we think the future of AI is local. Because most folks, I believe, I'm willing to bet the farm on, most folks will want their AIs to have access to this level of data, but they're not going to trust a remote vendor to aggregate all this data up on their remote servers and use that ethically, right? And this is also why I think that something that didn't really manifest in the 90s or the 2000s or the 10s is peer-to-peer software. It was always kind of like the dream. And outside of BitTorrent, which did see its heyday, and then Bitcoin, which is still part of the zeitgeist, peer-to-peer software never really went anywhere, at least not at the level I expected it to. Our computers don't really connect directly to each other anymore. They connect to a data center in Virginia, and we all rendezvous there, and we broker and exchange data through the data center. And I think AI is going to be the driver, where it's this level of personal, intimate access to your day-to-day life where people aren't going to be able to, or even willing to, delegate that to a remote server. They're not going to trust a bureaucrat in Washington or Virginia or a middle manager in San Francisco to determine what moral guidelines their children's AI tutor should have. Right? They want AIs that are hyper-aligned to them in their beliefs. And they want AIs that are aligned to them in the task that they are after, not whatever someone very remote, faceless, that they don't even know the name of, what their personal beliefs are. But in order for this future to happen, I think we're going to need to close the user experience gap between local and cloud. Because right now, I don't know how many of you actually host your own software. That's probably an outlier group, but hosting your own software at home has a lot of significant trade-offs. And those trade-offs, while for technical folks, we can usually overcome those, non-technical people have very little chance of being able to reliably self-host software. And just like simple user experiences that are like friends take for granted when they go online, like what happens when I go to the coffee shop? If I have a Mac Studio, which I believe by December, today's frontier models are going to be able to run on like consumer Mac hardware. But if I have a studio at home, and that's where my AI agent is running, and then I go to a coffee shop, when that AI agent is running in a data center in Virginia, it can go with me. I can have a conversation with it on my desktop, get up, go to the coffee shop, and pick the conversation right back up. Local software doesn't work that way unless you're standing up a personal VPN, right? Or a simple interaction like, hey, had a cool interaction with my LLM, and I want to share that with my friend. On hosted software, there's a button. You click it, you get a URL, you send it to your friend. They can click it, they can open it, and they see it. That's not as straightforward with local software today. Or I'm working on an AI agent. I taught my laptop a cool new trick. It can open Slack and let me know if there's any new messages from my coworkers. And I want to share this with my friends, or I want to work on this together, right? How do we collaborate on actions together if we're not rendezvousing at a remote server? How do they access something that's hosted on my laptop? And then there's an entire class of problems that I can sum up as you're the server now. And today, you're the server now requires you to be a system administrator, like uptime, managing connections, looking at logs, installing software, updating software. These are things that normal users or normal, like my friends, my family, they aren't going to be able to spend a significant portion of their life sysadminning AI software. And this is where, if you came to the talk last week, I introduced CRDTs, and I said I would show you how to take the server out of that flow. And I hope, or like, it's my hope that in the near future, it's going to be as simple as this: npm install p2p, and you can just go. But today, where it stands right now, it's not quite there. I think 2026 is going to be the year where it starts taking shape, and we have a lot of groundwork to do between now and then. And if you want to get into this, I've talked to a lot of people who have been casually interested in peer-to-peer software, and it's really hard to get into it because you look out at this landscape of peer-to-peer applications from BitTorrent to Git to Matrix, and it can be kind of overwhelming. They are very complicated pieces of software, and it's hard to understand how you plug them together to get anything done. And I think that's the problem, is that you don't plug these things together. These things are the result of plugging building blocks together to get the functionality that shows up in these products. It's like going out onto the web and saying, I want to build a website or a web application, and looking at Netflix and Living Spec and being like, okay, how do I plug these things together in order to get an application? That's not how it works. And you're not going to learn much by going through the front door of these things to try to understand how they're built, right? So really what we want for peer-to-peer software is an analog to something like this. Way oversimplified, didn't put much time into this, don't critique it. But just like a set of building blocks that we can plug together to get a web app up off the ground. And this is an abridged peer-to-peer building block list. I know it's intimidating. It's not as bad as it looks. And we're just gonna briefly touch on a few of these and kind of show mental models, how they work, and then how you can apply them and what they can be used for. And also how real world applications like BitTorrent and Bitcoin use these things. So we're gonna start with something that a lot of you are probably already familiar with, and it's hashing. So a hash, at its core, it takes a file, any random array of bytes, right? And it generates another array of bytes. Most hash functions that you're gonna come in contact with, that array of bytes that it generates is always the same size. So you can take any size file and you always get 256 bits out. And those 256 bits are gonna be unique. A good hashing function for the use cases that we're gonna be talking about today, you know, if you have two files, they should always generate two different fingerprints. Always is a loaded term because it breaks information theory, but for any practical file that you generally encounter, you should not run into what's called a collision, where two files hash to the same value. And if you wanted to play around with this today, you would find a library that provides SHA-256 hashing, which, as a byproduct of putting the slide or deck together, I learned is quantum secure, or considered quantum secure. Didn't know that, that was surprising. But grab a library that provides SHA-256 hashing, and you can start playing around with hashes. But as a building block, what can you do when you're playing around with a hash? You can do a surprising amount with just this one building block. One of these is a content address storage. Content address storage is used in a lot of systems. It's used in version control systems. It's used in decentralized storage systems like IPFS and storage. It's also used in deduplicating of files in large-scale data sets. If you hash the file, it's really trivial to see whether or not another file that matches that same byte is stored in your system, because it's going to have the same content address, and you can deduplicate it on disk doing this. And content address storage is fairly trivial to implement on a local laptop. You take your file, you pass it through your hash function, and then you store the file at the hash. And then later on, somebody comes along and asks for the hash, and you give them back the file. So you can implement this more than likely in a few lines of Node.js and get a feel for how you can use hash functions as a building block to put together cool and interesting behaviors. You can also use it in a much more interesting and maybe not obvious way, which is proof of work. And proof of work, I think most of us know it from like Bitcoin, but it's also used for denial of service mitigation. So like the Tor network uses it to shed load and prevent servers from getting overwhelmed. I believe DeepSeek does as well. I haven't verified that, but I've seen that on X. And the core of proof of work is you reach out to me asking me to do some unit of work, right? Like send you a file or render a web page. And I respond to you with the challenge. And that challenge should be very hard for you to solve and very easy for me to prove that you've solved it, right? So let's say I send you a challenge. This challenge is going to say prefix 42, and the difficulty level is 3. We're going to take the SHA-256 hash. Sorry, not SHA-256 hash. First, we're going to take 42, and we're going to represent it in a binary, which is 10, 10, 10. You can use that as a prefix of an array. And you're going to take that binary array, and you're going to just randomly generate a number. You're going to put it in that array, pass it through the SHA-256 function, and out the other side, you're going to get your hash. And the difficulty corresponds to the number of leading zeros in that hash, which corresponds roughly to the number of guesses you're going to have to make in order to find a solution to this problem. If you want people to spend more time, require more leading zeros, right? And you can give this a try. 2 functions, take a SHA-256 hash, right? Sit there, loop till you find the answer, and then write a function that validates it. And you can see one should run in almost instantly, and the other should run roughly proportionally, exponentially, to the number of leading zeros. All right, so we have 2 kind of fun things we were able to do with a hashing function. We're going to put it together with another building block here, which is encryption. Encryption is I think we mostly encounter it when we're trying to protect our data, like secure communication channels, encrypt our hard drives, etc. But it can also be used for identity. So I can prove to somebody that I'm in possession of a secret that nobody else is supposed to have. And as long as people know that I'm the one who's supposed to have that secret, they know that I'm the one who encrypted the file, right? It can also be used for proving that I actually did something. So if I want like an external auditor to be able to come in at some point in the future and verify that I've been honest, right? I can have a trail of things that I've attested to with encryption, proving that I've done or taken certain actions, right? And we'll show how to do that in a little bit. And there's really 2 buckets of encryption. At least I have 2 mental buckets that I put encryption algorithms in. One is symmetric and the other is asymmetric. Symmetric works like a standard locking key. I have a key, which we're going to call it a password, and I have an encryption function. And I use the password, pass it through the encryption function with some data, and it encrypts the data. Later on, I want to decrypt the data. I have a key. I can unlock it, right, and get my data back out. And if you want to play around with this, find a library that provides you AES encryption, and you can encrypt some data. Then there's asymmetric encryption, which I find way more interesting and generally more useful, which is also like a standard locking key. But unlike real-world locks and keys, this is kind of like a magical locking key where I have 2 keys. And when one of the keys locks a box, only the other key can unlock it, and vice versa. So if I take one of these keys and I call it my public key, and the other I call it my private key, right? And I take my public key and I give it to everybody. I post it on my website, put it on my DNS records from my email, etc. If you ever receive a box in the mail, right, you can take my public key and try to unlock that box. And if my public key unlocks the box, the box was locked with my private key. This works really well for like establishing identity, knowing that my device was the device that generated a message. This also works really well for establishing secure communication channels. I can lock a box, send it to you, you can use my public key to unlock it, and inside of there can be all the information necessary for us to establish an encrypted stream between 2 devices. And if you want to play around with this, find yourself a library that does ED25519 keys or Curve 25519 encryption. And there's a couple of them that are really good in the JavaScript ecosystem, and you can start playing around with these. But if you were going to play around with these, what would you do? Well, the first thing we can do with this is a blockchain. And I define blockchain a little differently than I think colloquially we do it. And I think I'm right, but that's neither here nor there. So a blockchain is a linked list, in my opinion. And it's a linked list that when we generate this linked list, we keep track of the parents and the children, right? Just like a standard linked list in computer science data structures. And at each node, we create what's called a block. And the content of that block, we're going to say first block 0, block 1, block 2, and then we're going to throw random content into it. Content can be anything, what your application wants to run, right? In this case, we're just putting standard key value pairs in there, right? But then we take, and this is why it's called a blockchain, we chain a hash. So what that means is block 0 doesn't have a parent, so we just hash its content. But block 1, we take its content and we prepend the hash from the previous block and generate a hash. And we do the same for block 2. What this means is if I change any of the content in block 1 or block 0, the hash of block 2 is going to change. So if I possess the hash of block 2 externally from an organization, right, later on I can come back and I can verify without ever having seen block 0 or block 1 that they have not been tampered with, that those blocks were the blocks that existed when block 2 was generated. And this is extremely useful. And then we're going to extend a little bit. This isn't part of a blockchain necessarily, but it's extremely useful in my opinion. We sign the hash, and by signing the hash, we can prove that the node that generated this block generated it, right? So later on, when I'm looking at the hash of this block, right, I can, or not hash of this block, when I'm looking at this block, I have some level of assurance that it was generated by the person I think who generated it. And when we talk about blockchains this way, not like the cryptocurrency way, what I just pitched to you is what was proposed by Dominic Tarr and Secure Scuttlebutt. So you could actually, at this point, if you've tracked with me so far, sit down and read the Secure Scuttlebutt paper, and for the most part, understand it. And you could probably implement like a working, functioning kind of pet project on top of this in about a week in between browser tabs, which would be kind of fun. So this can be used for social feeds, kind of like Secure Scuttlebutt does. It's a social network built on top of these chains that propagate between devices, and there's no, well, they didn't really successfully get rid of the server, but they decentralized the server in a way. It also works for external audits. So let's say I'm a financial institution and I interact with the public. Whenever I receive a request to do something, if I append it to my ledger and my transaction ID for that interaction is the hash that was in that block, I am now externally communicating a reference to my ledger to the public. Why this is useful is you don't have to be able to see my books, but at some point in the future, if I'm like subject to regulatory compliance, an external auditor can come in equipped with nothing but the transaction IDs that I've shared with my customers and verify that I'm not tampering with my books during an audit. So it's just like using a transaction ID as a hash, you can have like full external auditability. And when we talk about blockchains, there's a lot of blockchain solutions that do exactly this for industries that are highly regulated. And now we get to where most people use the term blockchain, which is when you take what I consider a blockchain and pair it with a proof of work scheme or some other consensus scheme. So we're going to take our proof of work building block from before, and we're going to take our blockchain building block from before. We're going to combine them. So we're going to take this blockchain, and inside those content blocks, instead of these key value pairs, what we're going to do is we're going to take transaction or statements of transactions. This user has sent this other user this amount of money, and it's going to be signed by the user that's authorizing the transaction, right? So I'm going to authorize, send 5 units of currency to this other user. Then what we do is we use proof of weight or work when we have a handful of nodes that are trying to keep track of this chain. We'll use proof of work to control the rate the blocks are generated. So if I only want 1 new block every hour, right? All of the nodes in this distributed system, they all target 1 block per hour for the difficulty. So if I have seen more than 1 block per hour, I increase the difficulty for me to accept a transaction or for me to accept a new block. If I've been seeing less than 1 block per hour, I decrease the difficulty. This lets me fine tune the difficulty based on the number of blocks that I would like to see. Whenever one of the nodes in this network discovers a block that matches the difficulty or discovers a nonce for a block that generates the hash that matches the difficulty, right? That generation of that block, when it's signed by that block's ID, you generate some unit of currency in the protocol says this wallet now has, 5 units of currency for finding this block, or 1 unit of currency for finding this block, and we call that mining. And in the off chance that multiple nodes discover the next valid block or find a solution to the next block at the same time before all of the nodes sync, right? So if you and me both find a block at the same time, we just let the blockchain temporarily fork, and the next miner, the next one who finds it or finds a block, picks one of those to append their block to, and eventually the longest chain wins, right? And at this point, you could sit down and you could probably read through this is a surprisingly short paper. The Satoshi paper is 4 pages long. And if you've been tracking with me, you could probably sit down and read those 4 pages and roughly understand what he's talking about. Now, if we take that building block and we pair it with doing useful things with the content of those blocks, I call that a utility coin. So Bitcoin has a certain utility. It allows you to transfer value, and it does it in a Byzantine fault-tolerant way. But it doesn't exactly, the work it's doing allows us to reach consensus, and that was novel at the time. But it's really just generating a bunch of SHA-256 hashes and then throwing them away. There are useful things you can do with that work. And one of the useful things you can do with that work is what Filecoin did, which is like part of the protocol, the challenges that you're, solving in order to get reimbursed for the work that you're doing on the network, is proof that you have agreed to store another user's file, and that at the time that that block was generated, you are still storing that file. So you use the data that was sent to the node. We're not going to go into how they do this, but use the data that was sent to the node to answer a problem, almost like a proof of work. It's the proof of storage. I've stored this file, and I submit that to the network, and that's how I get my reimbursement. Ethereum did something wildly mad science awesome at the time, and inside of those content blocks, what they did was they put opcodes for a virtual machine. And what this allowed you to do is, as the next node finds the next, or as a node on the network finds the next block, it advances the virtual machine state when it creates that transaction, which lets you basically have an on-chain computer that can run full programs, and all the nodes reach consensus about the state of that computer. So when they talk about smart contracts and stuff, it's this virtual machine executing opcodes, running programs, and advancing it every time a new block is generated. It's a little more technical. I'm way oversimplifying it, but the building blocks that are present in this paper, I don't think we've really covered. But if you're feeling brave and reading it, it's a really, really fun paper, and it's a completely different way of thinking about things. I know this has been intense. I'm sorry. We also have, I think this one is a little less intense. We had that blockchain data structure. It was just this chain of hashes, right? And there's this thing called a Merkle DAG. And a Merkle DAG is very similar, where you have this chain of hashes, and you can sign them like we did before. But instead of a linked list, we use a directed acyclic graph, which is a scary term, but it's a very simple concept. This is our blockchain, and this is a Merkle DAG. Merkle DAG is the same, or DAG is the same as a tree, except you can have multiple parents and multiple children. And the A in DAG is acyclic, means no matter which one of these circles you start on, if you follow the arrows, you can never end up back where you started. You can't walk in circles through the graph. If you walk in circles, there's a cycle, and it's no longer acyclic. And if you kind of followed what I just said, you know that directory on your computer, .git, every time you drop into one of your projects? It's full of all of this random gibberish. I think if you're tracking with me, you can now open up that .git directory and start making sense of it. So inside of the Git directory, internally they have these Git objects, and they're actually just content addressable Merkle DAGs. So they take the files, they hash the files, and they put them in a Merkle DAG, and that's your tree reference is an entry to a node in a Merkle DAG. And you can follow that Merkle DAG all the way through now. I believe, I haven't done this yet, but I believe you can open them up, and they're just standard text files. So you can cat them, open them up in Notepad, you can read them, and you can follow through the whole Merkle DAG. Don't quote me on that. So there's some very cool projects that we're on the verge of unlocking with this, but we're going to pause for a second to talk about clocks We're going to talk about clocks right now because there was something that was not obvious in the Merkle-DAG and the blockchain examples that actually equips us to solve a very difficult problem in peer-to-peer systems, which is getting everybody to agree on when things happened, right? And we need to be precise about what we mean when we say when things happened. If, we have, let's say we're talking about AI, right? We have a handful of users and they're all interacting with the chat, right? LLM, but they're all interacting with the same LLM. The order they interact with that LLM in, if they're offline and they're not talking to each other and then they connect and they start syncing events with each other, the order that they sync those events matters a lot for the user experience. In fact, if you open up your phone and your laptop and you set them next to each other and the conversation isn't in the same order, for a user, that's going to be really confusing, right? So we want everybody in a network to agree on the order that events happened in. And why we're precise here is that agreeing on timestamps can't be a goal because computers don't agree about they don't agree on what time it is. All of our computers have a slightly different definition in this room of what the time currently is. A few of our computers might have a wildly different definition of what time it is. And we can't trust it. On top of that, if you're wanting to order events and some of those events are actually important, like whether or not, let's say you're an enterprise organization running an AI software system and you want to say, hey, we just fired Bob and we fired Bob at 10 o'clock today and Bob should not be allowed to do anything after 10 o'clock, right? Timestamps aren't provable. So if Bob just says, I solemnly swear I submitted this event at 9:59 a.m., right? That doesn't work in that case. So we can't trust timestamps and they're not reliable to begin with. And the reason we can't trust timestamps, it's actually 50% solvable. It's really easy to keep secrets from the future, from the past. And that's because the future is there's a lot of entropy out there, full of possibilities and really hard to predict. So keeping a secret from the past is as easy as taking the headline off of today's New York Times and saying hey, when I generated this block, this was the headline. And we all know that you didn't have access to today's New York Times a week ago. So I know that this wasn't generated in the past, but when it comes to information, it is really hard to keep, it's impossible in my opinion to keep secrets from the future because anything that I know today that I could use to prove time, right? I can know tomorrow, I just have to remember it. So it's not really solvable in the other direction. So how do we order events when we can't rely on timestamps? And the answer is actually in this diagram. It's a bit of information that's not immediately apparent. It's the arrows. So the arrows aren't in that JSON object. And that was to simplify the block structure. But those arrows are the solution to ordering events. So if we put that in the object and we call it the parent, and we keep track of the hashes, we establish what was the state of the world when I made a change. So when block 3 was added, it was added after, block 2 was added, it was added after block 1. When we look at our Merkle-DAG, this is where things get extremely useful. We establish our list of parents, just like in a normal directed acyclic graph. And this node 0 hash, so the hash that was generated at block 0 from node 0, right? That hash, when you see the term dot vector clock, that's what that is. So a dot vector clock is basically just keeping track of what was the state of the world when I generated an event. And when we have this dot vector clock, what we can do is we can now order events. We know on our network that from this dot vector clock, that first block was generated first. And those middle blocks, they were generated concurrently. Even if those may have been generated, 5-10 minutes apart, from the system's perspective, they have to be considered concurrent because neither of those nodes had seen state prior, or seen the state of the other when they generated the event. And then finally, the final node was generated third. And now I think we have enough to tackle what I ran through about a week ago, or speed ran through a week ago. Oh, geez, CRDTs. So CRDTs, if two nodes are connected, we're actually gonna skip this because we are out of time. We're also gonna skip CAD. We're gonna skip IPFS. And we're going to skip NAT traversal. I'm so sorry, guys. This was way too much content. If you are interested in NAT traversal, I have a collection of essays on it at Blankenship.io. These were the building blocks we went over. And if you go back to the beginning when I said I would like to get us to a point where you can npm install peer-to-peer and just like start building the software, and I apologize that this was so dense. Part of the reason this is dense is because right now when you try to dive into this software and like building this stuff, it's very satisfying. Being honest, it's the most satisfying work I've done in my life. But you have to actually roll up your sleeves and understand what's going on the inside right now. It bleeds through. These abstractions bleed through. And unless you you don't have to understand how to build them yourselves. It's really fun to build them yourselves, but you have to roughly have a mental model of how they work in order to use the software. But you can npm install libp2p. And libp2p is a lot like the express of peer-to-peer software. It's this middleware layer where you can take behaviors like we were going to talk about Cadmelia or a blockchain, right? And you can plug them into this middleware stack. And then you can plug in TCP or UDP or WebSockets or WebRTC, and you can connect browser tabs. And then you can take the software, like these the software implementations of like Cadmelia, and wire them between. So this hopefully sparked a little bit of interest. If you are interested in playing around with this, hop over to libp2p's website and download it. And I think the future of AI is local, but it's not going to happen unless we build it. Like right now, the momentum in the industry is application service providers. They are ASPs. They've had 20, 30 years worth of head start on us. And that is what we're going to get out of AI. We're going to slot a server into a server rack, and we're going to get our 1984 telescreens. But we have an opportunity over the next year to change that trajectory. And I think that would be really cool. So if you were somewhat interested in this and you would like to plug into my stream of consciousness, this is where I post on X. And we didn't get to do the CRDT demo. That's okay. There is a, oh no, did I close it out? We don't have time. Afterwards, I have a GitHub repository set up. If any of this stuff was interesting and you want to explore the stuff, you want to do any of the demos in this, or you want to explore something similar, come talk to me. I'll give you the link to it. Create a directory on that GitHub repository, and you can start submitting merge requests to it that have your little pet projects or exploratory work, and I'll review that and give you feedback, and we can like work on this stuff together because we need more people working in this. So if this interests you and you want to work on this together, talk to me afterwards. Cheers, y'all.